Okay, the quiz is now too late to submit, which means I can go over it. But this is another one of those quizzes where you should know what you're aiming for, right? You're aiming for 2 pi r for this one, the formula for the circumference of a circle. And you're aiming for 4 pi r squared, the formula for the surface area of a sphere here, right? And I think over the weekend I gave you a hint as to what problems to look up that were very similar to it. Right? So there was a problem from 8.1 that was similar to this one. I think it was number 2. And I gave you a hint that there was a problem similar to this one from the previous work also. This was 8.1, this is 8.2. So anyway, okay, so solve for y. Y is radical r squared minus x squared. Okay, so that's this part right here if you're going from 0 to r. So this is a quarter of a circle. All right, so this is 0, this is r. So when I use the formula for arc length, I'm getting a quarter of a circle. And then I'll just simply multiply that by 4. All right, so dy dx is 1/2 r squared minus x squared to the negative half times negative 2x. 2's canceled out, comes out to be this. Square it, get this. Add 1 in the form of r squared minus x squared over r squared minus x squared. These cancel out, r squared over r squared minus x squared. So the arc length is the integral from 0 to r. You know the radius is r, so you're going from 0 to r of radical r squared over r squared minus x squared dx. Divide top and bottom by r squared. R squared over r squared is 1. Then in the bottom, r squared over r squared is 1. X squared over r squared I can write as x over r squared. Do a u substitution, that u equal 1 over r x. Du is 1 over r dx, means I need to put a 1 over r here, multiplied by r over here. R is a constant in this context. R is not a variable, it's a constant. Okay, so if x is 0, u is 0. X is r, put an r there, then u is equal to 1. So I now have an r in front, integral from 0 to 1 of 1 over radical 1 minus u squared. Ends up looking like this. So that's my inverse sine. So I have r inverse sine of u from 0 to 1. Okay, plug in 1, inverse sine of 1. Plug in 0, inverse sine of 0. Inverse sine of 0 is 0. Inverse sine of 1 is pi over 2. So I have pi r over 2. So this arc length is pi r over 2. So what's the circumference of an entire circle? Well, this is a quarter circle, so I just multiply by 4. So 4 times pi r over 2, 2 pi r, which indeed is the formula, as you know, for the circumference of a circle. Okay. So you notice in this class we're deriving a lot of the formulas that you had from 6th grade or 7th grade. Oh, circumference 2 pi r, area pi r squared, volume 4/3 pi r cubed. So where do you come up with these formulas? Okay, this is now with the techniques of calculus 2. That's where you get a lot of these formulas. And the surface area formula that we know is 4 pi r squared. Okay. So if I take the same region, spin it about the x-axis, I get half a sphere or a hemisphere. So I have to take my answer off to multiply by 2. All right, now the radical part is exactly the same. So I don't have to go through that computation again. It's radical r squared over r squared minus x squared. But if we spin it about the x-axis, it's 2 pi y that you multiply by. But y is radical r squared minus x squared. Okay. And notice very conveniently, these cancel out. Square root of r squared is r. So I'm just integrating 2 pi r. So that's very easy. So 2 pi r x from 0 to r. Plug in 0, you get 0. Plug in r, you get 2 pi r squared. So the surface area of this surface of revolution is 2 pi r squared. That's half a sphere. So the surface area for the whole sphere, you just multiply by 2. And you have the formula for the surface area of a sphere, 4 pi r squared. And there we go. Okay, so that was the quiz. All right. So 9.2, I was done with slope fields. And by the way, the quiz for Thursday, I was going to give you a slope field. Okay, so you get a slope field Thursday. Yeah, it takes a while, but you get to have the whole weekend to do it. So you have to make that table with 49 entries and then make the little stubs, those 49 stubs that we had, right? Stuff like that. And you have to make something like that and like that for me. Okay, and you'll likely have to do that in the exam also. Okay, so I will do 19 through 24. It's on something called Euler's method, E-U-L-E-R, and then maybe do 9.3. I could finish it all today. If I do, then we're done, but we're still not going to change the day of the test. Okay, so we are quite a bit ahead. So let's aim for the exam still being Thursday the 22nd. So if I go ahead, that's fine. Okay, so I will finish either today or Thursday, not an issue. Okay, and I think what worked fine like last time, and most of you seem to do better under those circumstances, so let's aim for the same thing. So Tuesday, I'll lecture, first hour, maybe like 10.1 or maybe 10.2, wherever it is. Okay. Second hour, I'll let you ask questions about the test for the entire second hour. Okay. That way, you may not have to ask as many questions on Thursday, and then we can start the test earlier, just like before. Okay, so let's make that our game plan. So lecture as normal today. I mean, originally I was only supposed to be at 9.1, but I'm way past that. Okay, lecture Thursday, wherever I end, I'll give you time to do the quiz. And let's make this strategy for next Tuesday. So first hour of Tuesday will be lecture. After the break, questions and answers. So then you can ask me anything you want from here. Okay. And then the following Thursday is a test. We'll see how it goes. I might lecture a little bit on more stuff, but we'll see how it goes. Now, I'll let you ask questions next Thursday, but just like the last test, if we get a lot of the questions out of the way on Tuesday the 27th, then maybe you won't have to ask as many questions on the 29th. Then we can just start the test earlier. And most of you seem to do better on the test under those circumstances. So let's aim for that for now, okay? All right, so any questions about that? Okay, I know some of you put something in the chat. I think I will go ahead and check the chat before I start any homework problems now. So unfortunately, I can't see the chat at the same time as I share the screen. Let's see. So what will be on the exam? The exam was 8.1 to 9.3, that break. Okay, so you know how I had the division? I can show it to you again after I go back and share. But there's a break in the homework for chapter 6, then there's a break for chapter 7, and then there's 8.1, 8.2, 9.1, 9.2, 9.3, right? So that is a natural break. So that's the coverage of the test. Then there's a chapter 10 test, and there's a chapter 11 test. Okay? And I think that's pretty much it from the chat. Yeah. Okay, so now I'm going to go back. Unfortunately, I can't do that fast, as a lot of you know. There's no fast way to do that. So I got to close down the chat again and go back to sharing the screen, where you have to click on that, click on that. You guys know what it's all about. Okay, so coverage of the test is here, 8.1, 8.2, 9.1, 9.2, 9.3. Okay. And yes, obviously there are more sections in chapter 8. There are more sections in chapter 9. We're not required to cover it, so we won't. Okay. And then the fourth test is just chapter 10. And then the last test is chapter 11, but you can see it's the biggest. That's the most nice stuff. Okay. All right, so let me get started with the rest of 9.2. So everything up to here was slope fields, and now 19 through 24 is something called Euler's method. So there's an algorithm that you have for Euler's method. Euler's method. It looks like Euler, but the pronunciation is supposed to be Euler's. All right, so again, we're already done with the first half of the section. So 1 through 14 was the slope fields, right? So last time, doing stuff like that. Again, you won't have to make this many. You only have to do 49, 7 times 7, going from -3 to 3 for for x and negative 3 to 3 for y, just like we did. Okay. So now what is Euler's method? So you start off with a differential equation, y prime equals, and then the right-hand side is a function of x and y, something involving x and y. And you also have an initial condition, like this, y of 0 equals 1. Okay. Now, you're going to use that information to guess what happens further on down the line. Okay. So suppose you wanted to estimate y of 1, let's say over here. Okay, so I'm on page 595. Okay, so y prime equals x plus y. That's my differential equation. So the left side is just going to be y prime or dy dx. The right-hand side is going to have x and y, maybe, and initial condition. So y of 0 equals 1. That means the point is 0, 1. That's like you drop the particle on 0, 1 that we're talking about last time. Okay. Suppose this is the actual solution. So red is the actual solution. So what's this blue thing? Okay, y of 0 equals 1. The point is 0, 1. What happens if I plug in 0 and 1? I get 1, right? Slope is 1. So what if I start off at this point and just draw a line segment that has a slope of 1? Okay, and I'm guesstimating what happens by the time I reach x equals 1. Okay, my guess would be over here. As you can see, it's off. Okay, so the real solution is the red, which we don't know how to get yet. My guesstimate, if I said, okay, well, I got a slope field. Right here, the slope is 1. Why don't I just go along that line and say that's my guess? Not very good, right? But, so that's called the first Euler approximation. Now, suppose we say instead of just doing a one-shot deal, I break this interval up into 2. The usual game in calculus, break it up into more pieces. So I'll go from 0 to 0.5 and then 0.5 to 1. Okay, so I start off with the same point, 0, 1. Notice it's starting at the same point. If I plug in, I still have the slope of 1, right? 0, 1, slope is 1. So I go along. So this part from 0 to 0.5 is exactly the same as this. But I stop when I reach 0.5, comma 1.5, I guess it looks like. And then I plug into the differential equation again. Okay, so I plug in 0.5, comma 1.5. So 0.5 plus 1.5, 2. So starting from here, I have a new slope of 2. Now this was 1 all the way. This one, halfway, I decided to switch over to a slope of 2. So as you can see, the approximation is going to get better. Right? This one just goes at a slope of 1 all the time. But halfway, it shoots it a little bit higher, so the approximation is better. Okay? And as you might imagine, if I let n go to infinity and delta x approach 0, then you keep recalibrating. As you keep recalibrating, right, the approximation gets better and better and better and better. Okay. Here they have a step size of 0.25. So look at what happens. I start off again with a slope of 1. I go out to 0.25, stop, take that x and y, plug it in. I'm going to get a new slope. So I go to new slope until I reach 1.5, stop, get that new point, plug it in. I get a new slope. Notice in this case, it looks like each time it's getting steeper. Stop at 0.75, and you have a corresponding y value. Plug in again, and so I've changed slopes 4 times, and you can see the approximation gets better and better and better. So if delta x was 0.00001, you're moving a very small amount and then recalibrating and recalibrating. So it would tend to be a very, very good approximation. Of course, I would never make you do, n is equal to 1,000,000. That's where you want a computer to do it, right? You can program a computer to do this very easily 1,000,000 times, and you can see how the approximation gets better and better. In fact, sometimes that's actually what's done. You can't get a hold of the differential equation, so the only thing you can do is a numerical approximation. So just have a computer do something like that, 1,000,000 times, and it can spit it out very quickly and give you an approximation that way. Okay, so this is Euler's method. Okay. Now, the author gives you this. I'll show it to you. It's correct. And if you want to use it, that's fine, but I'm going to show you my method. instead, which I think is more intuitive. You can just plug it in the formula. It works. I don't know what's going on, but I'll just plug it in, and there it is. Okay. So I'll try to give you a more intuitive feel, and so you can kind of get a feel of what's going on. So again, this is not wrong. It's not wrong what they're doing. 595 at the bottom, Euler's method. Okay. So it's y sub n equals y sub n minus 1 plus h f of x n minus 1 y n minus 1. You might even say, huh? I don't even know what it's talking about. Okay, so that's the reason why I'm going to give you my method. All right. Okay, so here we go. So how do you do this stuff? And so now the rest of the problems are 19 and 21 to 24. Okay, with Euler's method. And again, for the benefit of those of you who don't have the book and don't plan on getting it, there's 19 and 21 to 24 is over there. Yeah. All right, so here we go. So for 19a, you have a very easy differential equation. Y prime equals y, and y of 0 equals 1. Estimate y of 0.4. Okay. Now, so y prime equals y. That's my differential equation. This one's very easy. You start at y of 0 equals 1. You say, what's h? H is the same as delta x. It's a tiny change in x. 0.4, 0.2, 0.1. Okay, so you're starting at 0, comma 1. You want to estimate what happens at 0.4. The first approximation, delta x, h, is 0.4. So you're only going to have one computation because you're starting at 0, you're going to 0.4, and your step size is 0.4. So there's only going to be one computation. Very fast to do, but it's clearly not going to be that accurate. This one, delta x, h, is 0.2. So this time, how many steps am I going to take to get to 0.4? There's going to be 2 steps, a little bit more accurate. Part 3, 0.1. So my step size, my delta x is 0.1. If I'm going to go out to 0.4, I have to do it 4 times. More accurate, but as you can see, clearly there's a lot more work, right? So definitely a lot more work. All right, and let's see, I'm saying we're going to do B, but let's not worry about C. Okay, so let's skip 19C. So skip 19C. We'll do B, at least part of it. Okay, and let's see. Yeah, we're not going to draw anything either. So even for 19B, as in boy, we're not going to worry about drawing stuff. Okay, we'll just compare our answers. Okay. All right, so here's the idea behind Euler's method. Okay, so this is my version. Whoops. Yeah. Okay, y prime, we know it's a slope. Okay. Slope is delta y over delta x. Or if you multiply both sides by delta x, delta y equals m delta x. Okay. And if you want, you can put this on your cheat sheet because we're going to be doing this a lot. Delta x is, delta y equals m delta x. The change in y is equal to the slope or the derivative times delta x. Okay. Again, if we were meeting face to face, I'd make you guys memorize this. It's not that hard to memorize because if I cover up the deltas, it looks like y equals mx. You've already heard of that, y equals mx plus b, right? So it's not that hard to memorize y equals mx. Just put deltas in front. Delta y is equal to m delta x. Okay, here's the concept, but I think you have this concept already. X new is equal to x old plus delta x. Likewise, the y new is the y old plus delta x. This is like the x of n minus 1 and x of n minus 2 that the book was trying to show you. How do I get the new x? You take the old x and you add delta x. Makes sense, right? You have an old value for x, then you add a delta x, you get a new x value. Similarly, how do you get the new y value? Well, you take the old y value, and then you add or subtract your delta y. Okay, so we're given an equation, y prime equals a function of x and y. Okay, that looks funny to have a function of two variables, but you'll get used to that a lot when you take Calc 3. Okay, Calc 3, you have a function of multivariable. That's why it's sometimes called multivariable calculus. Okay. And by the way, a side note, some of you are wondering, yes, right now I am scheduled to teach Calc 3 in spring 2021. So that way you know if you want me, or maybe some of you don't want me as your Calc 3 teacher. But right now I'm scheduled to teach Calc 3 spring 2021. But anyway, that's beside the point. Okay, so you're given y prime equals, on the right-hand side, could have x and y, and some initial condition, like y of 0 equals 2. And then they'll tell you to estimate something, like estimate y of 1. Okay, so getting back to 19. So here's my differential equation, y prime equals y. This one is pretty simple because they don't give me x and y, it's just y. Y of 0 is 1. Estimate y of 0.4. Okay, so number one is very easy. There's only one computation, but it's probably not going to be very accurate. You're just going straight from 0 to 0.4. We're going to say, all right, whatever the curve looks like, maybe it looks like that, maybe it looks like that, maybe it squiggles around. I'm just going to get the slope here, and I'll just keep that same slope until I get to 0.4, stop, and that's going to be my guess. Probably not that accurate, right? All right, so n is 1. Number of times I'm doing it is just one time. Okay, as I mentioned before, when the second part, when h is 0.2, then n is 2. I'm doing it 2 times. My delta x is 0.2. And for the longest one, number 3, h is 0.1. That means I have to do it 4 times. Okay. So this one's going to be fairly quick, I think. All right, so I'm at 0, 1. What's my slope? I plug into the differential equation. Y prime is y. What's the y coordinate? 1. So the slope is 1. Okay. So at my beginning point, 0, 1, the slope is 1. Now, what's delta y? Delta y is m delta x. Okay. So put it on your cheat sheet, or if you want to memorize it, memorize it. Okay. Again, the way I would memorize it is you already know y equals mx plus b. So y equals mx. Just put a delta here and a delta here. So delta y is m delta x. My delta x is 0.4. I multiply that by 1. And so my delta y is also 0.4. And then I increment. I add up. Increment, I-N-C-R-E-M-E-N-T. I add where it was. So what's my new x value? I started at 0, 1. It's the old x value, 0, plus delta x, 0.4, which makes perfectly good sense. If I start at x equals 0, my delta x is 0.4. Well, now I'm at 0.4. What's the new y value? It's the old y value plus delta y. So what was my old y value? 1. What's my delta y? 0.4. So if I used to be at 1, I go up 0.4. Now I'm at 1.4. So my new point is 0.4, comma 1.4. So ultimately, we're trying to guess the value of y of 0.4. So our guess is that the answer is 1.4. So the answer to part 1 is that our estimate of y of 0.4 is 1.4. Probably not that accurate. Okay, so now I'll do part 2. We're going to break this up into 2 pieces. So that's like when the book did this. If I can find the page. So we've already done this one. Find the slope, go in a straight line until I reach where I'm supposed to find, stop. Calculations are easy, but not very accurate. Now they want us to break it up into 2 pieces. So halfway through the problem, I will recalibrate. Probably going to be a better approximation. The last one, n is 4. Do it 4 times. So go to 0.25, recalibrate, get another slope. Go to 0.5, recalibrate, 0.75, recalibrate. Probably more accurate, but obviously a lot more work. Okay, part 2. H is 0.2. That means delta x is 0.2. So now the picture is like this. Okay. I go from 0 to 0.2. I stop, I get a new slope, and then I go another direction. All right, so it starts off the same. Whoops, I'm over here. Okay, so I plug in 0, 1 to the differential equation. Plug in 1, the slope is 1. So it starts off exactly the same with a slope of 1. Now I keep doing this stuff. The new x is the old x plus delta x. Same thing for the y. The new y is the old y plus delta y. So I started at 0, 1. Whoops, I'm over here. 0, 1. Okay. What is delta y? Okay, so my m is 1. How did I get to 1? Slope means derivative. Y prime was equal to y. So I start off at 0, 1. I plug in 1 for y. Slope is 1. Okay, so what's my delta y? Delta y is m delta x. So m is 1 times 0.2, 0.2. So what is my new point? I started at 0, 1. My delta x is 0.2. So my new x coordinate is 0.2. How come? I started, the old x is 0, the delta x is 0.2, so now I'm at 0.2. What's the new y value? I take the old y value, 1, plus delta y, which is also 0.2, so 1.2. So this point right here is the point 0.2, comma 1.2. Okay? And now I stop and recalibrate a new slope. Okay, so I get a new slope this time. Okay, what's the new slope? I plug into the differential equation. Y prime is still y, so the new slope is no longer 1, it's 1.2. So it's a little bit steeper. So my slope is 1.2. Then do it again. Delta y equals m delta x. 1.2 times 0.2, 0.24. That's my delta y. All right, so what's my new coordinates? I take the old coordinates, add delta x, add delta y. So old x is 0.2. What's my delta x? 0.2. By the way, the delta x stays the same throughout the problem, right? So even at the get-go, you know delta x stays at 0.2. That never changes. I'm going to go from 0 to 0.2 to 0.4. Okay, so that's given right at the start. What's not given is the delta y's. Okay, I figured out the delta y was 0.24. So what's the new y? I take the old y, 1.2, add it to the delta y, 1.44. Okay, so my guess of y of 0.4 is 1.44. And I'm supposing this is going to be more accurate than what I had over here. So let's see, over here I had 1.4. By doing this game, I got 1.44. And we're going to guess it's probably more accurate. Okay, and then the third one, which is the most amount of computation, h is 0.1. That's my delta x. Same differential equation, y prime equals y, but now I have to do it 4 times. I'm starting at 0. And notice the x values are already predetermined. Even before you go on, you know you start at 0. My delta x is 0.1. So you're going to go 0.1, 0.2, 0.3, 0.4. 4 calculations. That's already set in stone. What I do have to figure out each time is the delta y's. Right? So unfortunately, I got to do it 4 times, but the computation is probably going to be more accurate. So I keep doing the same thing. Slope starts off at 1 because y prime is just y. Y coordinate is 1. So slope is 1. I always do delta y equals m delta x. So 1 times 0.1, 0.1. After that, I write here the new ordered pair. Okay, I decided not to draw this picture anymore. You don't really need it, but it's it's going to change each time. Okay, so what's the new point? I take the old x, add delta x, 0.1. I take the old y, 1, add delta y, 0.1, and that leaves me with 1.1. Okay, so this is the new point. And just repeat the process 4 times total. So I've done it 1 time. I need 3 more times. Okay, so here's my first point. Find the slope. Plug in 1.1. Again, delta y is m delta x. So 1.1 times 0.1, 0.11. This is my delta y. So what's the new point? 0.2. Again, the x values are already determined. Right at the start, 0, 0.1, 0.2, 0.3, 0.4. Okay. What's the new y? It's the old y, 1.1, plus delta y. So add that to that, 1.21. Okay, halfway through, 2 down, 2 to go. Do it again. What's the slope? 1.21, because the y prime is equal to y, 1.21. Do this again, delta y equals m delta x. You can put all this on your cheat sheet if you wish, or you can put some examples. You say, what do? I do this and this and blah, 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 blah. Okay, delta y is 1.21 times delta x, 0.1, 0.121. Okay, what's the new x? It's the old x plus delta x. Delta x is fixed, 0.1. What's the new y? It's the old y plus delta y. So I add 1.21 to 0.121, 1.331. 3 down, 1 to go. One more time. So how do I know to stop at 0.4? They told us to estimate y of 0.4 or f of 0.4. Okay, one more time. What's the slope? Well, since y prime or m, y prime is m, right? The slope is the same as the y coordinate, 1.331. Delta y is m delta x. I got it over here. Put it on your cheat sheet if you wish. So 1.331 times the delta x. Notice the delta x is the same for this one part, 0.1, 0.1, 0.1, 0.1. This comes out to be 0.1331. So what's the new x? Old x plus delta x, 0.1, 0.4. Then I'm done. What's the new y? Old y plus delta y, 1.4641. Clearly a lot more work, but we think it's going to be the best estimate. So part 3, y of 0.4 equals 1.4641. Okay, so look at the progression. N equals 1. Delta x is 0.4. You only do it one time. Just go in a straight line over there. 1.4. Chop it up into 2 pieces. 1.44. Chop it up into 4 pieces. Let's see, where'd it go? 1.4641. Okay, so the progression was 1.4, 1.44, 1.4641. Okay, now what about part B? Let's see, where'd it go? We know that the exact solution of this initial value problem is y equals e to the x. Okay, so all along, y equals e to the x is the solution. Okay, let's check it. Is it true that y prime equals y? The derivative is itself. The derivative of e to the x is e to the x. So it certainly satisfies the differential equation, right? Y prime equals y. Derivative is the same as the original function. Oh yeah, of course. Derivative of e to the x is e to the x. And is it true that y of 0 equals 1? Y of 0 and f of 0 means the same thing. So if I plug in 0, I get 1. That's true, right? E to the 0 is equal to 1. So don't draw the graph or anything. All that means is the exact answer is e to the 0.4. And then just for teaching purposes, I'll show you what that came out to be. Okay, so you can do this on your calculator, of course. So y of 0.4 is e to the 0.4. That comes out to be 1.49 roughly. Okay, so exact solution, 1.49 something. Let's follow the progression. N equals 1, 1.4. N equals 2, 1.44. So it got closer. N equals 4, 1.4641. Exact value, 1.49. So it is true that as n got bigger, the approximation got better and better. I'm guessing if you punch it in a computer, let it run 1,000,000 times, it would probably be very, very close to 1.49, whatever. Okay. All right, so that's how that one goes. Okay, I will show you 22 now. Okay, there actually aren't that many other problems. So I did 19. So 21 to 24, I'll do 22 for you. And let you see that. Again, I don't want to spend class time on computations, so I'll just show you all the computations. Right? But you punch it on your calculator yourself to see what it comes out to be. Okay. So 22. Use Euler's method with step size 0.2 to estimate y of 1, where y of x is the solution of the initial value problem. Y prime is equal to, let's see. I don't have the same thing as the book, unfortunately, so I'm going to have to change it. Okay, so sorry about that. So I'll give you my 22, which is unfortunately different. The delta x is the same, and estimate y of 1 is the same. Okay, so this is, I'll make this 22 star. And let's see, I keep forgetting our additions don't match. Okay, so I'll tell you what, don't do this 22. Okay, skip it. Just do my 22 star. Okay, so you're responsible for 22 star, which is problem 22 in the 7th edition, I guess it was. Okay, so it's not the same differential equation, so sorry about that. Let's see, I was going to show you a little bit of 23, and double check if that's the same. 23 actually is the same. Okay. I wasn't going to do all of 23, I'll just set you up with it, since you have the answer in the back of the book in theory. Okay. So 22 star. So again, don't do 22 in the book. Just learn my 22. You don't have the answer in the back of the book anyway. Okay, so they gave me a different differential equation, but this was the same, and this is the same. Estimate y of 1. Okay, now delta x is 0.2. I start at 0, I go to 1. That means I have to do it 5 times. Okay, n is equal to 5. How do I know it's 5? My step size, my increment is 0.2. So I got to reach to 1, so 0.2, 0.4, 0.6, 0.8 is 1. So I have to do it 5 times. Now, this is a much harder differential equation, xy minus x squared. In fact, the one that they made you do in the book is even worse. Yeah, it's real bad. Okay. So we'll just do this. All right, now, even right now, I know the x values. 0, 0.2, 0.4, 0.6, 0.8, and 1. There's no mystery. Because you start at 0, the delta x always stays the same, 0.2. So if I add 0.2 every time, I'm going to have 0.2, 0.4, 0.6, 0.8, and 1. So there it is, 0.2, 0.4, 0.6, 0.8, 0.1. The thing that you have to figure out are the y's from the delta y's. Okay, y of 0 equals 1. All right, so first I have to find the slope. So x is 0, y is 1. Take a look. If I plug in 0 there and 0 there, I get 0, right? Put a 0 here, 1 here, and 0 there. My first slope is 0. That's very nice. Which means delta y is also 0. It's m delta x, but no change in y. So my next point is 0.2 comma 1. The y coordinate stays 1 because my delta y is 0. So 0.2, 1. Now the computation gets tougher. What's the new slope? Plug in here. What do I plug in? I plug in x is 0.2, y is 1. So 0.2 times 1 minus 0.2 squared. Okay. Punch it in a calculator, 0.16. Again, I did it before. I'm not going to waste class time for that. But check to make sure you get the same thing. So my new slope is 0.16. Now how do I find delta y? Delta y is m delta x. So delta y is m delta x. So 0.16 times 0.2. For this one problem, the delta x stays at 0.2. And that comes out to be 0.032. Okay, so that's my new y value. The new y, sorry, that's my delta y. The new y value is the old y value plus the delta y. So 1 plus 0.032, 1.032. You can see the calculations get real messy after a while. Okay, so just keep doing it again. That's what, 2 down and 3 to go, I guess. So take that x and y, plug it in. Okay, so x is 0.4, y is 1.032. You can see the calculation gets real bad. So x times y, 0.4 times 1.032 minus x squared, 0.4 squared, okay, comes out to be 0.2528. That's an equal sign there. That's a new slope. Delta y is m delta x. So the slope is 0.2528. Multiply that by 0.2, 0.05056. In case you're wondering, don't round any of your numbers off until the very end. Okay. You guys have probably heard if you round off, many times, you get a rounding off of a rounding off of a rounding off of a rounding off, and that could lead to a big error. So keep every digit until maybe the very end. You can see it ends up being pretty bad, but it's the most accurate that way. And then only round off your final answer, perhaps. Say that. Okay. All right, so 0.2528 times 0.2 is 0.05056. So what's my new point? The new x value is 0.6. That's already predetermined, right? 0, 0.2, 0.4, 0.6. What's the new y value? I take the old y value, there it is, add delta y. So old y plus delta y is 1.08256. Okay, and you just keep doing it. Looks like I got to do it 2 more times. Okay, so I didn't bother writing it this time. You can just take my word for it. But I plugged in 0.6 for x, 1.08256 for y. I plugged it in here, grind it out, and this is what it came out to be, 0.289536. Okay, so 0.6 again goes here and here. You got to square it. And 1.08256 goes in here. Crank it out. This is what you get. One more time, delta y is equal to m delta x. You keep doing that. So take the m times delta x, which is 0.2. Now you have 0.0579072. Okay. Yeah, you probably only want to do it one more time. And that's about it. Okay, 0.8 comma, what's my new y value? Old y plus delta y. So 1.08256 plus that mess is 1.1404672. Notice I'm keeping every single digit. Fortunately, I'm down to the last iteration, the last try. So that's about it. Okay. Take that x, take that y, plug it in. Okay, it's not very fun. 0.27237376. And there we go. Delta y equals m delta x. Okay, so I take that multiplied by 0.2, 0.0544, blah, 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 blah. Finally, I reached what I was looking for. Asked to estimate y of 1. So 1 comma, the new y is the old y plus delta y, right? So 1.14, blah, 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 plus 0.05, blah, 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 is that. So you can write it all out, but now you can afford to round off since we're done. So our estimate of y of 1 is approximately 1.19, and we'll just leave it at that. Okay, so this is the basic idea behind Euler's method. I see it's about 8:05-ish. So I'll just blab a little bit more. Just disappear. Let me check 23, and is that what I had? 23. Y prime equals y plus xy. Y of 0 equals 1. Yes, that is the same thing. Okay, so I was only going to do one iteration of that, and then I'll just say etc. And I'll probably do that after the break. But let's get the fundamentals down. Okay, step size is 0.1. Estimate y of 0.5. So it says y of 0 is 1. Okay, so you're going from 0 to 0.5. That's 0.5. The step size, that's delta x, 0.1, which means how many times do we have to do it? 5 times. So you have to do it 5 times. Okay. So after the break, I'll probably only show you one of those because, once you get the hang of it, you pretty much got it. Okay. So I'll do that, and then I'm pretty much done with the section. And then maybe I can start doing some of 9.3, I guess. Okay. All right. So let's take a break. Oh, sorry. Somebody had something in the chat. So let me check the chat. Let's see. Is my Calc 3 online? Oh, yeah. All of CCSF math courses are online, so it's probably going to be just like this. And the schools are allowed to be open. You're right. It's pretty much it. Assuming spring 2021 is exactly like this, then yeah, same thing. It'll be just like this. If we meet on campus, then we'll meet on campus. I guess we'll find out. I mean, the way things are going nowadays, it doesn't look like it, right? Because nothing's open. Public schools aren't open. Colleges aren't open. So, I'm not, unless something miraculous happens and we get a real quick vaccine or something like that, I think we're all going to still be doing this for Calc 3 in the spring. Okay, so yes, that's my answer to that. And I think that's it for the chat right now. Okay, so let's break. Let's see. Well, it's a little bit after 8. About 8:15. Around 8:15, we'll pick up again. All right, so break time. I will disappear also. Okay, folks, it's 8:15, so we'll go ahead and start up again. And let's see, nothing extra in the chat, so I think we're good. Let me see if I can get back to sharing the screen. And here we are. Okay, and by the way, reminder, from now on, I think I'm just going to record all the way through. If I shut off the record, during the break, I might forget to turn it back on. So I thought to avoid that, I'll just record all the way through. So the recordings are always going to have that 10 or 15 minute break. So I apologize for that. So, but you can just fast forward if you're looking back at the video. But to make it easier and less chance that I'm going to forget, once I record, I just leave it alone until the day is done. Okay, so there's going to be that 10 or 15 minute break in the middle where nothing's going on. So sorry about that. All right, so I was going to set up 9.223, but not do it all. Probably just do one iteration until you get the idea, and then just move on. Okay. So, and let's double check that it does match. So use Euler's method, step size is 0.1, yes. Estimate y of 0.5, and the differential equation is y prime equals y plus xy. Y of 0 equals 1. So yes, looks like we have it. Okay, so delta x is 0.1. So I start at 0. By the way, do we always start at 0? No, you don't always have to start at 0. But I just, the ones we've been doing start at 0. So if delta x is 0.1, I have to do it 5 times. I'm going to increment, I-N-C-R-E-M-E-N-T, increment 5 times. From 0 to 0.1, 0.2, 0.3, 0.4, 0.5. Okay, so I'll just show you once, and then I just stop and say, etc. But you pretty much do the same thing all the way through. It's a different differential equation. Okay, so the first time I plug in 0 and 1. Okay, so 0 and 1. So x is 0, that means that's nothing, and y is 1. So the first slope is 1. Okay, delta y equals m delta x. So 1 times 0.1, 0.1. So what's the new ordered pair? X moves from 0 to 0.1. Y started off at 1. I'm adding 0.1, so now I'm at 1.1. Okay, it looks like I did it one more time, so I'll just do it one more time, and that's about it. Okay, so again, m is the same as y prime, right? Y prime gives you the slope of the tangent line, and that's m. So y plus xy, so 1.1 plus xy is 0.1 times 1.1. Okay, so again, y plus xy for this differential equation. 1.1 plus 0.1 times 1.1, grind it out, 1.21. So that's my new slope. Delta y equals m delta x. So 1.21 times 0.1 is 0.121. Okay, so the new point is 0.2. Take the old y, add delta y, 1.1 plus 0.121 is 1.221. Okay, and then I'll just say etc. I did 2 of the iterations. Just keep doing the same thing. Find the new slope, get my new delta y. Okay, get a new point, get a new slope by plugging into the differential equation, right? And then get a new y value and just keep going. Okay. All right, so that's about it. And now I'm ready to start 9.3. Something called separable equations. Page 599. Separable equations. So what are separable equations? All right. For this section, anytime you see y prime, change it to dy dx, the so-called Leibniz notation. That's Leibniz, Leibniz. Leibniz is one of the co-founders of calculus along with Sir Isaac Newton. So write it as dy dx. Okay. Treat dy and dx as something called differentials, right? They're very tiny change in x, very tiny change in y. Okay. What you want to do is write it as f of y dy equals g of x dx. Okay. Somehow, write y prime as dy dx. By means of algebra, can you get all the y's and dy on one side and all the x's and dx on the other side? Okay. If we can write the equation as this, then it's called separable. It's what's called a separable equation. Okay. The concept's not really that hard, I think. I think you'll find it's not so bad. Okay. So you have a differential equation. You might see y prime. Write it as dy dx. Okay. Using algebra and treating dy and dx as if they're their own variables. Okay. I mean, you can think of dy as delta y, where delta y is really, really, really small, and dx is like delta x, where delta x is really, really, really small. Okay. By algebra, get all the y's on one side with dy, get all the x's on the other side with dx. Okay. If you can do that, it's called separable. As you might imagine, all the problems in 9.3 are separable. Otherwise, they wouldn't give it to you. So if you can make it like this, then all you do is you integrate both sides. Integral f of y dy, and that's perfect, right? That's the way it's supposed to look. You've got a bunch of stuff with y and dy, then you integrate a bunch of stuff with x dx. Okay, then after that, solve for y if possible. Okay, so I'll show you some of those now, but again, I'm not sure if these problems double check with the problems in the book. Okay, so let me show you problems in the book and see if they're the same. First, let me just show you the book. So page 605. Let's see, you're only supposed to go as high as what? The largest problem was 23, it looks like. Okay, so it just is one page. Okay. So where am I in the book? Page 605. Okay, so you can check the recording for those of you that aren't going to get the book. And some more. And I think that's pretty much about it. Okay. So let's see. I don't even have this problem numbered. Yeah, so it doesn't really matter. So 9.3, I'll just say this is a first example. So this is not in the book, or not in 8th edition of the book. It says dy dx equals xy squared. Okay. Now, your object is to get all the y's on one side with dy and all the x's on the other side. So I will multiply both sides by dx, comes over here, and I'll divide y squared on both sides. Okay, so it's going to look like this. dy over y squared equals x dx. Okay, so that's the same thing, right? So I'm going to integrate both sides now. dy over y squared equals x dx. Okay, so I'm separating. F of y dy equals g of x dx. Get all the y's on one side with dy. Get all the x's on the other side with dx. Okay, so I'll make this y to the negative 2 dy equals integral of x dx. Okay, this is y to the negative 1 over negative 1 plus c1. We've talked about that before. There's a c1 and a c2. Integrate this side, x squared over 2 plus c2. Okay, but you can see if I just put these together, if I subtract, I would get c2 minus c1, which is still just a c. All right, so even though technically you're supposed to have a plus c1 and c2 on the other side, normally we'll just have the plus c on the side that isn't the y. Normally we're trying to solve for y. Right? Technically you don't have to solve for y, you could solve for x, I suppose, but that's the concept. So I'll just put a plus c here. Okay, now algebraically solve for y if possible. This is like negative 1 over y equals 1/2 x squared plus c. You multiply both sides by negative 1. Okay, now here's a concept I think you have to watch out for, that you have to get used to. Okay, so if I multiply by negative 1, I have 1 over y. This is negative 1/2 x squared minus c. Okay, but c is just any real number. So if I have minus c, it's the same as plus c. So I might as well just write it as plus c. Okay. It's almost like if you have a plus c, you can sweep a lot of algebra under the table, so to speak. Okay, it would say minus c, but minus c runs through all the real numbers. So if minus c runs through all the real numbers, so does plus c. So you're allowed to just leave it as plus c. Okay, now you can reciprocate both sides. If two things were equal, the reciprocals were equal, right? That's the fastest way to solve this. So reciprocate 1 over y, we have y. The reciprocal of this is 1 over the whole thing. So it's 1 over negative 1/2 x squared plus c. And note very carefully, if I take the reciprocal of this, the plus c is part of the denominator, just like we said at the beginning of the chapter, right? In this particular case, the plus c isn't hanging off to the side over here like we're used to. It's now part of the denominator. Okay, and just make it look nicer, multiply top and bottom by 2. So y is equal to 2 over negative x squared plus 2c. And again, 2c is just c. Okay, so this is an acceptable answer, but maybe it looks a little bit nicer if you factor out the negative 1 and put it like that. So negative 2 over x squared plus c. So that's my answer. So y equals negative 2 over x squared plus c. Notice this is our first attempt to actually solve a differential equation. Okay, yes, we actually are solving this differential equation. dy dx is equal to x y squared. Okay. So y is equal to that. And just for fun, so to speak, let's actually check to see if this works in the original example. Okay. Which really becomes like section 1, show and tell. Show that this thing works. Okay, so this is y. I'm going to write it as negative 2 times x squared plus c raised to the negative 1. So the derivative would be positive 2, right? X squared plus c to the negative 2. And then by the chain rule times the derivative of the inside, which is 2x. Remember, c is a constant. So clean that up. That's 4x over x squared plus c squared. Okay, notice the placement of c. C can be any real number, but it's not plus c hanging out over here like we're used to. It's part of the denominator right here. Okay, so let's figure out x, y squared. So x, y squared is x times, here's the original y, right? Negative 2 over x squared plus c squared. Okay, so what does that give me? That gives me 4x on the top, x squared plus c squared on the bottom. And lo and behold, it is equal to y prime. So it does satisfy the original differential equation. The derivative is equal to x, y squared from show and tell. So yes, indeed, this works. So we have an infinite number, an infinite collection of solutions. Just pick a different c and you have a different answer. Okay, and all of these functions satisfy the differential equation because it worked in general for c. So now that it works for any c, it works for c is 1, 2, 3, a million, pi, e, negative square root of 2 over 2, whatever you want. So there we go. Okay. All right, so yeah, it looks like my 5 isn't the same as the book's 5, but it illustrates a similar principle. Okay, so it's okay. I mean, it's not unusual for teachers to lecture not doing problems in the book, right? So just assume that's what's happening now. I'm lecturing with problems that are not from the book. It was from the 7th edition, but you know, we're still learning stuff. Okay, and it's actually not that much different from number 5. They have a trig function. Instead of sine, they had cosine and some other weird stuff like that. So I claim this 5 is sort of similar to this 5. Okay. All right, so y plus sine y, y prime equals x plus x cubed. Okay, so the first thing to do is write this as dy dx. and then you just multiply both sides by dx. So that way the left-hand side will have a bunch of y's, dy, equals a bunch of x's, dx. So there it is. Y plus sine y dy equals the integral of x plus x cubed dx. Perfect. Looks like this. F of y dy, a bunch of stuff that only has y and a dy, and then a bunch of stuff that only has x and a dx. All right, so we integrate. Integral of y is y squared over 2. Integral of sine is negative cosine y. Okay. So now we know, again, you don't have to put the plus c1 and the plus c2. Just put it on the side that doesn't have the y, namely the x. So x squared over 2 plus x to the 4th over 4 plus c. Okay. Now, solve for y if possible. There is no way to solve this for y. When you have a polynomial mixed up with a trig function, impossible. Which is actually better for you because that means we're done. I don't have to try to isolate the y. Like over here. Over here, it was possible to isolate the y, so you should do so. We found out y equals whatever. There's no way to isolate the y here because you have a polynomial tied up with a trig. So that's it. You're done. Just leave it alone. Okay. Then let's see. I'll show you 9. I think number 9 matches. Just looking dp dt. Yes, number 9 does match. So this one is an exact match, looks like. Okay, dp dt is t squared p minus p plus t squared minus 1. Okay, if I use the language of y and x, dy dx, so p is functioning like y, t is like the x. So I'm going to try to isolate the p, ultimately, is what I want. Okay, what you want to do here is factor by grouping. You remember factoring by grouping from algebra, right? There's 4 terms here. I factor here. I don't really want to factor this. There's nothing to do here. If I factor out the p, I have p times t squared minus 1, right? I am going to sneak in a 1 here. 1 times t squared minus 1. So this is factoring by grouping. So you might recall from algebra, now I can factor out t squared minus 1. So take that out. T squared minus 1, p plus 1. Okay? Now I can separate. Okay, so p is like y, so I'll put it all over here. So divide by p plus 1, multiplied by dt. Right, so multiply by dt, it comes here. Divide by p plus 1, it comes here. So I have dp over p plus 1 equals the integral, equals t squared minus 1 dt. So all the p's on the left side with dp, all the t's on the right side with dt. Okay, then I integrate both sides. Okay, so this is ln, absolute value of p plus 1. Again, don't need a plus c here, only over here. T cubed over 3 minus t plus c. Okay, so right now, it looks like that. Solve for p. Get rid of the ln. How do I get rid of ln? Exponentiate. E. These guys cancel out. Absolute value of p plus 1. Okay, I'm going to choose to split this up like this. E to the 1/3 t cubed minus t times e to the c. Okay, you might not be so comfortable going from here to here, but if you stop and think about it, you probably went this way a lot, right? So start from here. If you have e to something times e to something, you're supposed to add these, right? So there it is. Well, I'm just going backwards. It's just that normally in your algebra class, you didn't go like that too much. But you can see, you can go from here to here. Okay, now here's the nice thing about c again, arbitrary constant. What is e to the c? E to the c is still just c, still just another constant. So the next step, I'm just going to put c right over here. Okay, so again, if c is a constant, 3, 5, 80, negative 21, e to that number is still another constant. So the next step, I'm going to have to go up, but it just has a c in front. So it looks like this. Absolute value of p plus 1 equals c e to the 1/3 t cubed minus t. So all I did was I left all this alone. That's the same. I just put a c in front. Looks like this. Okay, now how do I get rid of absolute value? I just dropped it. Okay. And what allows me to go from here to here? Okay. So quick timeout on that. Absolute value of x is the same thing as x if x is greater than or equal to 0, but it's equal to negative x if x is less than 0, right? The absolute value of a number is the same as a number if I have a number greater than or equal to 0. Like, what's the absolute value of 7? 7. What's the absolute value of 0? 0. What's the absolute value of pi? Pi. If I plug in a negative number, the absolute value is the opposite of the number. So what's the absolute value of negative 4? Positive 4. What did I do? I did this. I did the opposite of negative 4. Negative, negative 4, right? Okay, bottom line, absolute value of x is either the same thing as x or it's the opposite of x. Okay, now how do I apply that to here? Okay, absolute value of p plus 1. It's either p plus 1 or the opposite of p plus 1. Okay. If it's equal to p plus 1, there it is. Okay. If it's equal to the opposite of p plus 1, so watch this logic. Okay. If it's equal to opposite, it's negative parentheses p plus 1. Okay. I know, I'll write it here. It would look like this. Equals c e to the whatever. Is that right? Yeah. And then multiply both sides by negative 1. It looks like this. So I have negative c. But what is negative c? It's still just c. See, you can sweep a lot of calculations under the rug when you have c. Okay? If you have c plus 5, c. c1 plus c2, c. e to the c, c. 3 times c, c. So it's still p plus 1 equals c e to the 1/3 t cubed minus t. All right, bottom line, for these problems, if you have an absolute value, as long as there's a c on the other side, you can just drop the bars, okay? So in short, you can just go straight from here to here. You can drop the bars, and the logic is it's either p plus 1 or its opposite. If it's p plus 1, it looks like that. If it's the opposite, if it's negative parentheses, we'll just multiply both sides by negative 1. You have p plus 1 equals negative c, but what's negative c? It's still c. Okay, so again, the nice thing about having c is you can sweep a lot of stuff under the rug. E to the c is c, c plus 4 is c, c1 plus c2 is c, right? Negative c is c. Okay, then just subtract 1. P is equal to c e to the 1/3 t cubed minus t minus 1, and we're done with that one. Okay. All right, then let's see. I want to do 11, and I see my 11 is not the same as your 11. So I guess that would have to be 11 star. It's a nice one. And let me just check something else. I was going to do 13, and 13 does seem to match. Okay. So anyway, 11 star. dy dx equals x over y. This time they give me an initial condition, y of 0 equals -3. Initial condition. That means my final answer should not have a plus c. I can figure out what the c is. Okay, the best way to do this is to cross multiply. That times that equals that times that. Very nice. Y dy equals x dx. Before I integrate, cross multiply. Y dy equals x dx. So I have a bunch of stuff with y dy equals a bunch of stuff with x dx. So I integrate both sides. Y squared over 2 equals x squared over 2 plus c. Multiply both sides by 2. Y squared equals x squared plus 2c. What is 2c? C. Okay. It's nice to do math when there's that plus c. You can just kind of forget about a lot of the other stuff. Okay, square root both sides. Y equals plus or minus the square root of x squared plus c. And now they say y of 0 equals -3. Okay. That means when x is 0, y is -3. And by putting -3 here, that automatically tells me I throw out the positive. That's kind of weird. We're used to throwing out the negative when I have a plus or minus. But in this case, in order for this to be -3, I have to throw out the positive, right? This isn't going to work if I have the positive, only if it's negative. Okay, so y of 0 equals -3. If you want to know how to read that, cover this up, and it says y equals -3. Okay, so that means that's x. So 0 goes here, -3 goes here. So -3 equals negative square root of 0 squared plus c is c. Square both sides, c is equal to 9. All right, so we got it. So the one and only one function that works is y equals negative square root of x squared plus 9. And a quick double check. What happens when you plug in 0? Put a 0 right there. Negative square root of 9 is -3. It works. Okay, and just for fun, I did show and tell because you're saying, does that actually work? Well, let's try it. It has to satisfy this differential equation, right? The derivative, dy dx, is equal to x over y. Well, let's try it. So here's the original y. Negative radical x squared plus 9 is negative x squared plus 9 to the 1/2 power. Okay, so dy dx is -1/2 x squared plus 9 to the -1/2. Then by the chain root times the derivative of the inside, which is 2x. Okay, 2's cancel out. I get -x over radical x squared plus 9. And what is x divided by the original y? So it's x divided by that. So it's x over negative radical x squared plus 9. And yes, indeed, they match. Okay? So we've proven that this is a solution to the differential equation with show and tell, like section 1. Okay? So here is a function, y equals negative radical x squared plus 9, which does satisfy this differential equation of y dy equals x dx. Okay. Okay, and let's see, what else was I going to show you? Yeah, 13, they use U and T, but it's the same thing. And 13 does match my 13, so I'll go ahead and show you that one. du dt equals 2t plus secant squared of t over 2u. U of 0 equals -5. And while I'm at it, I was going to show you 17. Also, y prime tan x equals a plus y. Y of pi over 3 is a, yeah, 17 we match. Okay, so that's going to be fine. Okay. Right, so du dt equals all of this. So u is functioning like y, t is functioning like x. So I'm going to try to isolate u. Okay, cross multiply. If I cross multiply, I have 2u du equals 2t plus secant squared of t dt. All the u's on one side with du, all the t's with dt. Then you integrate. Notice when you integrate, it's tailor-made, it's all set, and you even have the du and the dt the way it's supposed to be. Okay, so that's u squared. Integral of 2t is t squared. Integral of secant squared of t is tangent of t plus c. Square root, plus or minus. U equals plus or minus the square root of t squared plus tangent t plus c. And there we go. And now, once again, plug in u of 0 equals -5. So I can find the value of c. Okay, so plug this in for t, plug this in for u. And if you forget, say which one is which, you kind of cover this up and it says u equals -5. Then you say, okay, that's u, that means that has to be t. So 0 goes right there and right there. -5 goes here. So -5 equals, and once again, in this case, I have to throw out the positive. There's no way this is going to come out to be negative if I had a positive here, right? So I have to force this to be negative, so I throw out the positive. So 0 squared plus tangent 0 plus c. Tangent of 0 is also 0. So we get -5 equals negative radical c. Square both sides. C is equal to 25. Right? So final answer does not involve a plus c. And by the way, notice we didn't know this at the time in section 1, but now it's proving out. Yes, it is not unusual to have a plus c not hanging off to the side here like we're used to, right? We're used to saying blah, 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 plus c. But now the plus c can be under the square root. It can be under the fraction. It can be all over the place. Right? That's just the way it turns out. So I just plug in 25 and we're done. So u is negative square root of t squared plus tangent t plus 25, and we are done. Okay. And let's see, what else did I want to do? 17 doesn't match, I think. 17, y prime tan x equals a plus y of pi over 3 equals a, and we're between 0 and pi over 2. Okay. We don't really need this. It's just a quote-unquote nice angle. First quadrant, right? Okay, just checking here. 19 does not match, unfortunately. But that's the way it goes. 23 does seem to match. Yeah, okay, that's good. All right, so y prime, make it dy dx. Okay, so I want the, and by the way, a is just a constant. So divide by a plus y, multiply both sides by dx, and divide by tan x. Okay, so that's what all these arrows mean. Okay, dx comes here, multiply. A plus y comes down, divide by tan. So it looks like this. If I divide by a plus y, it's over here, dy over a plus y. If I multiply by dx, it's over here. And then on the right-hand side, I have 1 over tangent x. But 1 over tangent x is cotangent x. Okay, so this is ln, absolute value of a plus y. Okay, integral of cotangent x. Okay, you can memorize it or write it down, but you can make it a substitution, call it cosine over sine. Then just do a u substitution. U equals sine x, du cosine x dx. Call that I1. So I1 becomes integral of du over u, which is natural log absolute value of u plus c. Change it back. So ln absolute value of sine x plus c. Okay, so put that over here. So now I have natural log absolute value of a plus y, that, the same as that, equals ln absolute value of sine x plus c. Okay, we've played that game before. Okay, solve for y. How do you get rid of ln? Exponentiate, e. That cancels out. That cancels out. Remember, this is like before. This is e to the c. What's e to the c? C. So I have absolute value of a plus y equals c absolute value of sine x. Okay, and I mentioned this before. When you have that c, you can just drop all the bars. Drop that bar, drop that bar. A plus y equals c sine x. Okay, the same logic as I showed you earlier. Okay, so subtract a. So y is equal to c sine x minus a. Okay, now they want me to find out the c. So I plug in y of pi over 3 equals a. So y is a, the x is pi over 3. So put pi over 3 right here and a over here. So I have c sine pi over 3 minus a equals a. Okay, sine of pi over 3, sine of 60 degrees, radical 3 over 2. Add a to both sides. 2a equals c radical 3 over 2. Multiplied by the reciprocal of radical 3 over 2, 2 over radical 3, 2 over radical 3. So c is 4a over radical 3. That weird number. Okay, and that gets plugged right back over here, and then you're done. Okay, so there it is. Y equals 4a over radical 3 sine x minus a. Okay. All right, I noticed 19 doesn't match, so I have to say 19 star. But it's similar. It's not that much different. I got dy dx equals xy. They change it to x over y. Okay, not that big. And yeah, it says find equation of the curve that passes through the point. So that's your initial condition, 0, 2. Okay. In my 19, it was y of 0 equals 1. Okay, so you're still learning the same thing. It passes through 0, 1. Okay, so dy dx is xy. Divide by y. Multiply by dx. So dy over y is equal to x dx. Integrate. Integrate. ln absolute value of y, 1/2 x squared plus c. We know the way the game works. Get rid of ln by putting an e, exponentiate. Absolute value of y, e to the 1/2 x squared plus c. Just like before, just put the c in front. It's e to the 1/2 x squared times e to the c. And then e to the c is just c. And we know how this works. Just drop the bars. You can only do that when you have a c. Don't just drop the bars arbitrarily every time and say, oh, my teacher said I can just drop the bars. No, that's only when you have that c here. Yeah, again, the logic is absolute value of y is either y or negative y. If it's y, there it is. If it's negative y, put a negative here, multiply both sides by -1. You have y equals negative c, blah, 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 blah. But negative c is still just c. Okay, then to find the value of c, I plug in 0, 1. Y of 0 is 1. Okay, x is 0, y is 1. Put a 0 right there and a 1 right there. If you forget which one is which, okay, kind of cover it up and it says y equals 1. So y is 1, that means that's x. So 1 equals c e to the 1/2 0 squared. That's e to the 0 or 1. So that means c is 1. So we have it. Y equals e to the 1/2 x squared. The problem's finished, but I'll dig deeper. It says y of 0 is 1. Is it true when you plug in 0, you get 1? Put a 0 right there. E to the 0, 1. Let's also check the differential equation. dy dx is x times the original y. What's the derivative of this? It's the same thing, then by the chain rule, times the derivative of this, which is x. So it's x times e to the half x squared. In other words, it is x times the original, x times y. So it definitely fits. Show and tell, so to speak. Okay, 23, and then I think I'm done. What time is it? It's almost 9 o'clock. So I'll do 23, and then guess what, folks? We're done with everything for the test, which is not going to be until next Thursday. All right, so you have plenty of time. So I guess theoretically, I could have given you the test this Thursday, but no, I'm not going to change the date. Okay, so I will have completed everything you need to know for the test by tonight, once I finish 23. And it says no graph, don't do any graph, whatever that means, but I'll show you that in a second. So once I do 23, I'm done, and then I'll let you ask questions. It's a little bit after 9 when I'm done with that. And so the rest of the time I'll let you ask questions. If you don't have any questions, then we're done. Okay, so it looks like I'll get started with chapter 10 on Thursday. I'll let you have a lot of time for question and answers. How about Thursday and next Tuesday? So as I keep going ahead with chapter 10, maybe do a section here and a section here or whatever, I'll give you question and answer time. So that means once again, by the time the test comes next Thursday, where it go here, then maybe you don't have as many questions, and then I can give you more time for the test. Okay. Right, but again, it looks like I'll be able to finish everything tonight. So coverage for the exam is everything up to today. And I'll get started with 10.1, I guess, on Thursday. And of course, I have to give you time to do the quiz. And the quiz will just be a slope field. You'll make the table of 49 and put the 49 little stubs. And you might be asked to draw solution curves also. Okay. 23, no graph, whatever that means. That means skip part B, right. So solve the differential equation. Oh, I better double check. Is it the same as mine? Yes, this one is the same as mine. Skip B. Oh, sorry, take it back. I am going to do B, but not graph. Solve y of 0 equals 0. Does the initial value problem y of 0 equals 2 have a solution? Explain. Okay, so I will do A, B, and C, just not the graphing part. Okay. So I'll be done within the next 5 minutes, so maybe by 9:05. So at that point, I'll let you ask questions. So if you think about questions you might want to have, bring it up or put it in the chat. You can even put it in the chat now, and that'll take us until the rest of the evening. And if nobody has anything, then we can just call it a night. Okay, so y prime is equal to this thing. So when it says y prime, call it dy dx, then we separate. So divide both sides by radical 1 minus y squared, multiplied by dx. So if I multiply by dx, I have 2x dx, divide by radical 1 minus y squared, dy over radical 1 minus y squared. Okay, all the y's with dy, all the x's with dx. Then you integrate both sides. This is inverse sine function. Inverse sine of y equals x squared plus c. Again, normally you only need to put the plus c on the side that doesn't have the y. Okay, you saw the first example, right? You could say plus c1 plus c2, but just put the c1 and c2 together and it's just a c. Okay, how do I get rid of inverse sine? I take the sine of both sides, because sine of inverse sine would cancel out, right? So sine both sides. So y equals sine of x squared plus c. All right, that's that. And then part B, I guess I should have put part B here. Said y of 0 equals 0. So the initial value is y of 0 is 0, and then they want you to do y of 0 equals 2. Okay, so put a 0 here and a 0 here. Y of 0 is 0, put a 0 there, 0 there. 0 equals a sine of 0 plus c. Okay. Well, what nice angle do I want behind my pen here? Sine of 0 is 0. So I want behind my pen to be 0. It is 0 plus c. That means I want c to be 0. So y equals sine of x squared. That's that. Now, what are they asking for part C? This ready here. It says, does initial value problem y prime equals blah, 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 y of 0 equals 2 have a solution? Explain. Well, let's just figure out what happens if y of 0 equals 2. So 0 goes in for x, 2 for y. If you forget which is which, just kind of cover that up. It says y equals 2. So 2 goes there, that must be for x. So 0 plus c is c. It would say sine of c equals 2. Sine of what angle gives me 2? Well, that's not possible. We know the sine of any angle has to lie between negative 1 and 1 on a unit circle, right? All right, so that's why this is not possible. Can't happen. And there we go. All right, so I'm done, folks. I'm done with all this. So again, Thursday I'll start 10.1. And now let's see if anybody has questions. So let me stop here and check the chat for anything. Okay, 8.2, number 9. Okay, so maybe I'll write some of these down. 8.2, number 9. Anybody else want to put something down or from the chat? Let me look at what else was on the chat. I think I've caught up. Okay, 8.2, number. Anybody else? Because I can't see the chat while I'm sharing the screen at the same time. So anybody have anything there? Well, you can ask later, but I'll have to go back and forth. Okay, so right now just 8.2, number 9. Let me see what that's about. Eight point two, number 9. Okay, wow, so it looks like it's this one. So y squared equals x plus 1. 8.2, number 9. Y squared equals x plus 1 between 0 and 3. And we're spinning it about the x-axis. Okay. I think I got it. All right, so that means y equals square root of x plus 1. Okay. And this is a surface area of revolution. So dy dx, this is x plus 1 to the 1/2. So dy dx is 1/2 x plus 1 to the negative 1/2 times the derivative of the inside, which is just 1. It's 1 over 2 radical x plus 1. I'm supposed to square it. So if I square this, I have 1 over 4 x plus 1, which is 1 over 4x plus 4. Then 1 plus dy dx, quantity squared, is 1. That's 1, right? Plus 1 over 4x plus 4. So that looks like 4x plus 5 on top. Okay, so surface area is integral from where to where? 0 to 3. 2 pi Okay, if I spin it about the x-axis, it's 2 pi y. If I spin it about the y-axis, it's 2 pi x. We said that before, right? So on 2 pi y, and y is this thing. Radical x plus 1 square root of 4x plus 5 over, okay, 4x plus 4 I will factor out as 4 times x plus 1. And watch what I do here. 2 cancels square root of 4, radical x plus 1, radical x plus 1. Take out the pi. So pi integral from 0 to 3 of 4x plus 5 to the 1/2 dx. Okay, you can do a substitution, but I think you can just go straight to it. So 4x plus 5 to the 3/2 divided by 3/2 means times 2/3. And then by the chain rule, if I were to differentiate this, I multiply by 4. Since I'm integrating, I multiply by 1/4 from 0 to 3. So cancel, cancel 2. That's going to be pi over 6. Okay, plug in 3. 4 times 3 is 12, plus 5 is 17 to the 3/2. Plug in 0, 5 to the 3/2. So it looks like pi over 6, 17 radical 17 minus 5 radical 5. So that looks like the answer for that one. Okay. All right. So again, if I'm ever going too fast, you can watch the video. And of course, the video you can pause anytime you want, go backward, forward, and so on. So it's showing everything here, I think. Okay, stop the share. And let's see. Okay, if you got the right answer and it's valid and you did a different way, that's fine. That'll be perfectly fine. Okay. Looks at 27. Okay, I can't vouch for that. Okay. Well, let's see. 27. I don't know, maybe. So what was it? 8.2, number 9? Try that. 8.2, number 9. What am I doing? I'm looking in the back of the book. 8.2, number 9. You're right, it says 27. And that doesn't make sense because they shouldn't have an answer radical 27. Because radical 27 is reducible. Okay, so I'm sticking to my guns. I'm just going to leave it as this. And 17 radical 17. Okay, so anyway, that's that. Okay. 8.213. Okay. Eight point 213. X equals 1/3. And can't read it. Y squared plus 2 to the 3/2 power. Y goes from 1 to 2. And you're spinning it about the x-axis. Okay. Go through this again. Hit that, that. Okay. So if you spin about the x-axis, it's going to be 2 pi y, right? Same logic here. It seems to be easier if I integrate with respect to y. They already have x as a function of y. The limits are with y. So when I put down 2 pi y, I don't have to change it like I did over here because I'm going to integrate with respect to y. Okay, so dx dy. So let's see, 3/2 times 1/3 is 1/2. Y squared plus 2 to the positive 1/2. Then by the chain rule times the root of the inside, which is 2y. Let's see, 1/2 cancels 2. So I have y radical y squared plus 2. Is that right? Cancel y, yeah. So 1 plus dx dy squared is 1 plus y radical y plus y squared plus 2 squared, which is 1 plus y squared plus 2, which is y to the 4th plus 2y squared plus 1, which very conveniently is y squared plus 1 squared. That's the whole idea behind this problem, to make it nice. Okay, that goes underneath the square root, and you can see when I put that under the square root, it's very nice. Okay, so surface area is integral from 1 to 2 pi y. But this time, since I'm integrating dy, I leave it as a y. Okay, now you might say, oh, how come I didn't do that over here? It's still 2 pi y, but I was integrating with respect to x. So right here, I was not allowed to leave it as y. There's going to be a there's going to be a dx there. So I had to change it to x. Here, I'm integrating with respect to y. I just leave it as 2 pi y. And then square root of this thing, dy. And the square root of a square, of course, just take that off. Take out the 2 pi. So I have y times y squared plus 1 dy. And that should be pretty easy, I hope. 2 pi integral from 1 to 2. Let's see, y cubed plus y dy, which is 2 pi y to the 4th over 4 plus y squared over 2 from 1 to 2 equals 2 pi. Paren, paren, minus paren, paren. Plug in 2. 2 to the 4th is 16. 16 divided by 4 is 4. Plug in 2. 2 squared is 4. 4 divided by 2 is 2. Plug in 1. 1/4 plus 1/2, which is 2 pi times 4 plus 2 is 6, minus 3/4. 6 minus 3/4 is what? 5 1/4. That's what? 21. 20. Let's see. 21 over 4. Cancel the 2 with the 4. 21 pi over 2. Okay. Show you that again. All right. So, let's see. Do we have anything else? Okay. Nope. All right. About 9:15-ish. Okay. Anybody else with something? Or else we can call it a night. It's up to you. Nope. Had enough? Okay. We're ahead, so we're good. All right, let's call it a night then. So next time I'll get started with 10.1, but that won't be on the test. Coverage for the exam is everything up to today, but we won't have the test until a week from Thursday. And I'll try to give you some time for questions and answers both on Thursday and Tuesday. Well, Thursday I have to give you the quiz, but definitely next Tuesday. Okay. All right, that'll do it, folks. So have a good night. See you next time. Okay. Good night, everybody. Bye.
Bye, Mr. Hom. Good night.